What? Okay. Trailed right into the beginning of that recording. I love that for me. So, for posterity, this is the final exam review, part 2 for spring semester of 2024. So, we had made it as far as question 7 in part 1. So we'll get started on question 8. Seems like the next place to go. And we're going to go back to arc length, something we haven't seen in quite a while. So we want to find the exact value of the arc length of a circle with a central angle of 100 degrees and a diameter of 4 feet. So let's start by going back to the equation for arc length. Voice crack there. That's happening in a minute. S equals r theta. Right. All the way back to, I think this was worksheet number 1. We had this equation for arc length, which is just some portion of the circumference of a circle. And we said that arc length is going to be equal to the product of the radius and the central angle. Oftentimes we'll say that having a central angle with a central angle means it is subtended. It's just a vocab word so that you don't get tripped up if you see that on the final. I don't remember which way I wrote it. So sometimes I say with a central angle, sometimes I say subtended. Just heads up. But cool. So we've got this S equals r theta formula. We need to be able to plug stuff in. So we need a radius and we need an angle. Now that angle is going to be 100 degrees, but we also need to remember that this formula only works if theta is in radians. We must have a degree in radian in order for that formula to work. So we'll need to convert it here. So to get that actual arc length, I want the radius, which is half the diameter. That's 2 times 100 degrees, which was my angle, times pi over 180. Hopefully we haven't forgotten that conversion factor, but just 1/2 circle divided by another 1/2 circle gets us to pi over 180. And if we simplify all of that, 2 times 100 times pi divided by 180, I got 10 pi over 9. And since our diameter is in feet, our arc length will also be in feet. So option C. 10 pi over 9 feet. Okay. And up next, back to some polar coordinates. So we're going to be given a polar equation, r equals 4 secant theta, and we want to turn that thing back into its rectangular form. So that means re-express this equation using x and y instead of r and theta. That's going to be our goal. And I will start by bringing together all of the formulas that we have for converting between rectangular and polar coordinates. They are, the big one, r squared is x squared plus y squared. Just the Pythagorean theorem, but for x and y. Then we can define both x and y with x equals r cosine theta and y equals r sine theta. And lastly, we'll have one equation that doesn't depend on r at all. Tangent of theta is y over x. So we'll use those 4 basic equations, make some substitutions, and hopefully get this thing back to in terms of just x and y. So first thing I'm going to do when trying to solve this thing is I want to rewrite it to be 4 times cosine theta. R equals 4 cosine theta, rather than 4 over secant theta. Right. It's easier to just have things in terms of sine and cosine as we try to make substitutions, and dividing by secant is the same as multiplying by cosine. So I'll make that substitution first. Next, there are always a few different things that you could do when we're trying to solve or switch an equation like this one. Anytime we see r floating by itself, it's usually nicer to express that in terms of r squared somehow, rather than having to resort to a square root of x squared plus y squared. We can do that sometimes, just it's not always the most exciting way to express an equation. Especially because we usually have to introduce some kind of a plus or minus there, and it's awkward to deal with that. So if I see r floating by itself, I usually want to do something to fix that. Also, anytime I see a sine or a cosine by itself, I'd like to somehow attach an r to one of those trig functions, because then I get a nicer substitution for x or for y. So sometimes I'll have, like, if I just had r equals 4 without the cosine theta there, I would probably square both sides and say r squared equals 16. Then I get x squared plus y squared equals 16, which is the equation of a circle, kind of like we'd expect. But if I have an equation more like this one, where I've got r equals 4 cosine theta, squaring both sides wouldn't exactly be helpful, because I don't want to square the cosine. So instead, I'm going to start by multiplying both sides by r. It's a fancy trick that'll help make the substitution easier in a moment. If I multiply that through both sides, my left side becomes r squared, just like I wanted. And my right side can be 4r cosine theta. And then I have a much nicer substitution for both r squared and r cosine theta. Okay, so on the left, I have r squared, which is x squared plus y squared. And on the right, for r cosine theta, that's just 4 times x. I'll also just slide it over so I keep my equal sign in the same spot all the way down. And now everything is in terms of x and y, so I'll go probably look for an equation that hopefully has that in it. And looking at my boxes, I do indeed have option E. X squared plus y squared equals 4x. Just like it came together. So since this part is multiple choice, I might be able to go through and look at some of these answers at the beginning and start deciding that maybe I don't like some of them, just on principle. If I need to convert this thing back to rectangular coordinates or its rectangular form, that means the only two variables I should have are x and y. Those are my rectangular variables. R and theta are both polar variables, so I should not have them present in the equation when we're done. So things like the entire top row, A, B, C, and D, all of those are mixing R and X and Y. So I know none of those could be a rectangular equation because they don't have rectangular variables. Even though, for example, option C, R squared equals 4x, that is the equation we have. We did find R squared is equal to 4x, but I can't use R in my equation. So I also have to substitute R squared for X squared plus Y squared in order to get it back to an actual rectangular form equation. So yeah, just a heads up on maybe what that problem might look like on the exam. All right, and with that, we got to the end of the multiple choice section of the practice exam. Let's look at some of the more free response stuff. And the first one, we're going to be asked to solve a triangle. So this is the stuff we've been doing quite recently. This one looks like it's probably law of sines. And the nice thing about this one, it gave us two angles right off the bat, so we don't have to do any checking for extra triangles. But I know two of the angles to start off. I know that this one's gonna be easy. or, as easy as a solve the triangle problem comes. So if I've got two angles already, I just would want to find the third one first. And I know that all three angles in a triangle have to add up to 180. So angle A, my missing one, must be 180 degrees minus the other two, minus 34 degrees, minus 63 degrees, and let's see, that's 180 minus 97. So 83. What I get? 83 degrees. 83 to 97 gets us back to 180. So that'll work. And I'll just drop that in the box right now. A equals 83 degrees. That was one of the things I need to find. With my leftover time, I should figure out what my last two side lengths are. I started by knowing what length A is. Now I've got to get length B and length C. So let's get B first. B divided by the sine of 34 degrees. The 3 comes first in 34, because I know how to write stuff. Equals, I want to set this thing equal to some other ratio in the law of sines. And I need to go with the one that I already know everything about. So I'm going to want to go to side length A. It's the only length that I have. So this will be 3.2 divided by the sine of angle A, which we just solved for. It was 83 degrees. To get B by itself, multiply that sine 34 to the other side. So B 3.2 sine of 34 degrees divided by the sine of 83 degrees. And I can go punch that into a calculator. Make sure you're in degree mode because we're using degrees for our angles. I just punched that out ahead of time. I got 1.80. A was measured in inches, so B should also be measured in inches. 1.80 inches. And lastly, I've got to go get side C, and I'm going to be a little bit lazy about it. I'm going to take the entry that I just put into my calculator for B. All right, I said B was 3.2 times the sine of 34 degrees over 83. The math works out almost identically for side length C. I just need to replace all of my B's with C's. So instead of length B, I'm solving for length C. And instead of angle B, I want angle C. So I'll just swap those two pieces, right? Just go back into that entry I had in my calculator already, change the 34 degrees to 63 degrees, and I'll get my answer. 2.87 inches. Come and put that in the box too. 2.87 inches. And that means I'm done. Solving the triangle means I just needed to find the three missing pieces. And there they are. Angle A, side B, and side C. But I saw earlier this was a 16-point problem, so I'm expecting probably some more work to show up here to justify the full 16 points. And it does have a part B. So in addition to solving the triangle, I also want to find the area of that triangle. So off a formula sheet, I'll go find one of my area equations. I'll just use the first one that says area is 1/2 of A times B times sine C. So in each of those area equations that relate back to the ABC triangles, each area equation has all three letters show up once. So AB sine C seems like it ought to do the trick. So I'll go to 1/2 of something times something else times the sine of a third thing, and then see what we get. So going back up to the top, A was 3.2. Right, that was in our given information. I solved for B. I got that it was 1.80. I'll just simplify to 1.8. And C was 63 degrees. Move that a little bit closer to my box. I just need to plug all those things into a calculator and it'll spit something out. 2.57 is what I got. 2.57 square inches. So if you're doing the problem on your own, and if you follow my exact numbers, you should get the same thing, 2.57. But if you used a different area equation, maybe you involved side length C instead, you might get an area that is very close but slightly different to mine. When solving for the area, we did have to plug in a number that we had already rounded to get there, right? I already had to round length B to 2 decimal places, which means when I use that number in another calculation, the rounding that I did in part A is going to affect the answer in part B. So depending on let's call it how severely you rounded in the first part, it could change your answer slightly for part B. So you get something that's close, but not exactly 2.57. It's probably just a rounding error or a rounding difference. Won't really call it an error, but a rounding difference. And we'll account for that on the exam itself. So as long as you're within like 1% of my answer, you're in a good shape. And 1% is bigger than it sounds like it is. All right, let's take things back to graphs of sine and cosine. So first question I want to pose for a second. Just think about it for a moment. I'm also going to move that thing off the screen so you can't see that. If I were to ask you a question, not telling you what the form of this graph is, right? I'm not going to tell you what kind of an equation it is. Look at it right here. If I were to ask you, is this graph a sine graph, a cosine graph, or some other third option? I want you to think for a second about what the answer would be. Like, if I'm asking the question, is this a graph of sine or a graph of cosine or something else? Come up with your answer for a second. And if you picked something else, that would be the most correct answer in this spot. Without any additional information, this graph could be either sine or cosine. So the most correct answer to the question I just posed would be there's not enough information to tell if this is specifically sine or specifically cosine. Right? Sine and cosine have the same shape. The difference between them is where within the phase the graphs start. So the phase being the position within a period that a graph of sine or cosine starts from is the difference between a sine and a cosine graph. But simply looking at this wave, I could express it either as a sine function or as a cosine. So just a preview into what maybe one of the exam questions is going to look like. This could be either sine or cosine. But if I want you to come up with a full equation, I'm going to specify which one I want, just to make things a little easier on ourselves. So on this graph, on this problem, I said I want you to come up with a sine equation. So we'll treat this graph like it's a sine graph, and we'll come up with the missing letters A, B, C, and D. So let's do that. In fact, we don't even need to look at the sine or cosine part until the very end. For now, I need to come up with the amplitude, the period, the range, and the vertical shift. I'm going to save the phase shift for last. But I just need to read some stuff off the graph. I think it's easiest to get the range first, because we just have to look at the maximum value and the minimum value. So maximum value is up here, minimum value down here. We're told that both the x scale and the y scale is 1, so we tick mark as 1. That's nice. So this maximum value up here, 1 less than 9 is 8. And then 2 below the x-axis is -2. So my range is -2 to 8. -2 to 8. And from that, I want to go get the amplitude and the vertical shift. The amplitude is half of the range, or half the length of the range. The range has a length of 10, from -2 up to 8 would be 10. Half of that is 5. I'll justify my answers a bit more in a second. The vertical shift then is the number that is exactly in the middle of the range. Exactly in the middle of -2 and 8 is +3. I'm going to start by just filling those two things in, and I'll come back and justify them. But for now, that holistic approach can be kind of nice. And I think it's helpful to look at the center line, which I know is at y = 3. So I'll draw that in. I'll label that line to y = 3. That'll be helpful as I'm trying to figure out what my phase shift is. But cool, that's everything that I can gather from the from the range. I'm going to develop that just from there. So the next thing I'll want to read off the graph is the period. So the period is the length of one full cycle. I think the easiest way to find the period is to look at the distance between two maximum values. So I'm looking at the length of this horizontal line. Period would be that line right there. That distance is the same as the distance between two minimum values. Two minimum values. So the period is also that length right there. And if I needed to, I could also get the period by looking along the center line. So really, I can look at any two similar points within a cycle, just get the distance between them. Just be careful if you're going to use the center line to find the period. Because if we're doing that, we have to skip over a spot in the middle. Right, in order to get a full period, we have to get one full peak and one full valley. So we can't just stop halfway through. So just if you do end up with a graph where you've got to read along the center line, make sure you skip a spot in the middle. Go 1 over each. So all three of those distances are the period. And we should actually go put a number to that. If I count up the boxes here, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes times the length of 1 is 8. So I get the period, it's 8. Another way I could have done that calculation. Well, again, I had 1, 2, 3, 4, 5, 6, 7, 8. I'll mark that in. Counted up those boxes. I also could have found the x value at my two maximums. My first x value is at -1. My second one is going to be out at 7. The distance between -1 and 7 is 8. Also a valid way to figure out the period. But again, just need the length of that distance. And suppose can't really dance around it anymore. I have to pick a phase shift. So phase shifts on sine, right? So let's pull this back up here. We know I'm trying to create an equation for a sine graph. So I need to pick some point where this graph hits its center line, somewhere along that yellow line I drew in. I think the easiest option is going to be this point right there. And I'm picking it that way because that's the beginning of a standard sine cycle. Right, I'm at the middle and I'm moving up. So if I measure from the green spot, the green point I just highlighted, and trace my graph through for one full period, I'll get the sine shape I'm used to seeing. So I think that's the best option for the phase shift, but there are multiple options and all of them could be counted correct. So in addition to that green point, I've also got any of these other magenta points that I just circled in. Anything that falls along that yellow line is a phase shift for sine. But I'm going to use the green one. It's out there at -3. Okay. So let's go find A, B, C, and D. At this point, I've read everything off the graph that I need to. I just need to work with the values I've got left. So I said I'd justify my answers from earlier. So let me do that. Let me go get the amplitude. In its formula form, this is y max minus y min divided by 2. That's the difference between the maximum and minimum values. And then take half of that. I came up with 5. That mean. Color those in purple since I got them from the range. To get the vertical shift, looks very similar to that equation, except it's the average value between the maximum and minimum y value. So instead of 8 minus -2, I need 8 plus -2. And again, those numbers are coming from right here. I missed the 2 that time. So that's the actual mathematical calculation I could have done to find 5 and 3. Or if you just want to justify it by saying half the length versus the number right in the middle. I think that conceptually makes more sense and is easy to remember. But there is a formula you can just plug stuff into if you prefer it that way. Cool. So what's next? We should get B. That requires a little bit of work. B, or the angular frequency, is another name for that value of B. And again, if you've taken a physics class, oftentimes this is a lowercase omega instead of B. Lowercase omega looks like a W. But we usually use A, B, and C here because A, B, C, and D. Because it's easier to remember. We don't really need too many Greek letters yet. But cool. 2 pi divided by the period is B, so 2 pi over 8 gives me pi over 4. So I'll fill that in for B up here. Pi over 4. And the last thing we need is C, the phase, which is related to the phase shift. And just to remind ourselves what that formula looks like, C is B multiplied by the phase shift, which is going to look like pi over 4 times -3. So that's the value we got for phase shift. It's -3. Multiply those together, nothing simplifies. It's just -3 pi over 4. All right, and lastly, let's get A. Save that one for the very end. I know the number for A is going to be 5, but I have to decide if A is positive or negative. And the positive or negative value on A all depends on the phase shift that I selected. I chose to start my graph at -3. And I chose that one because sine starts off with its normal pattern there. That's positive sine if I start from the green point. I'm starting at the middle and going up. Means A is +5. If I had chosen 1 to be my phase shift, so that first magenta circle right next to the green one, if I had chosen that for my phase shift, I would have a negative sine graph because I'm at the middle, but I start going down first. So negative sine, I would have chosen -5. But for ours, it's +5. So the final thing is to just put this all together in an equation. So 5 sine of pi/4 times x. Here's where I go minus c. So if I scroll back up to the top real quick, remember that it's minus bx minus c on the inside of the equation. So the sign changes inside the equation itself. So since c was -3 pi/4, I'm going to add 3 pi/4 right there. It's plus 3/4, 3 pi/4 on the side. And the very last bit, +3. Cool. And that's my whole equation. Oh, yeah. And we look at the next one, we're going to get to verify a trig identity. Oh, yeah. Oh, yeah, that is not that. So I'm glad we at least get to this one while we're still in class. I want to solve this thing. I'm going to work just on one side. And I'm going to work going down because it's a lot easier to do all those steps. So I want to work on the more complicated side, which to my mind is the right side. A bit more going on over there. So I want to start on the right side of the equation. First up, in fact, the first step on any one of these trig identities is to ensure that all of my angles are the same. I don't want to work with multiple different angles because that's a headache. So I want to use some identities that will first let me get rid of the pi/2 minus x and the negative x. Let's get everything back in terms of x all by itself. So cosecant of pi/2 minus x, that calls for a cofunction identity. And the cofunction to cosecant is secant. Secant and cosecant are cofunctions. So that's the first one dealt with. Then cosine of negative x. Cosine is an even function. So that'll be just cosine of positive x. Cosine of negative x, cosine of positive x are the same. So secant x minus cosine x. And I want to start combining these two things together. The other step that I would take, if I had one, I'd try a Pythagorean identity, but that's only if I have square trig functions. Don't have that right now, so Pythagorean identity is out. I changed all of my angles over. They're all just x, so that part's done. If I run through all those steps, don't see anything to do next, try changing everything to sines and cosines. That is often a step that is helpful when solving these things out. So I want to do that. Secant is the same as 1 over cosine x minus cosine x. Cosine was already cosine, so I didn't change it around. But now I do at least have a fraction that I'm trying to add in here. Right? My first function has a denominator, or my first term has a denominator. So if I want to keep simplifying this, probably getting a common denominator between the two terms is my next best step. That common denominator is cosine. So I'm going to multiply that right term by cosine over cosine, getting me to a new equation. 1 over cosine x minus cosine squared over cosine, all of x. After that, I now have two fractions with the same denominator, so I can combine them. I'm looking at 1 minus cosine squared divided by cosine. Now my numerator looks like a Pythagorean identity. So I'll change that guy over. I'm looking at sine squared over cosine. And at this point, I used my Pythagorean identity to change 1 minus cosine squared around. I've already changed everything to look like sines and cosines. I should remind myself what I'm trying to set this thing equal to. It's been a minute since I've looked at that. So come back up to the top. My left side was tangent x over cosecant x. So I'm just going to bring that back down. Tan x over cosecant x. And probably if this were an exam question, this would be as far as I would ask you to simplify. Maybe I would have called that, tangent x times sine x or something. But the next couple of steps are a little bit more than I'd asked for. But to just finish off this identity, making sure that this thing looks like tangent times cosecant, I am going to separate it out to be sine x over cosine x. Times sine x over 1. Right, I know I've got two sines in my numerator, so I could just, instead of calling it sine squared, I could call it sine times sine. And my justification for that is I'm trying to make my right side look like a tangent and a cosecant. Tangent I know is sine over cosine. Cosecant is 1 over sine. So I want to separate things out kind of like this. I'm trying to group a sine and a cosine together so that I can write down a tangent function. That was my motivation for this step because it's a little weird. But so sine over cosine is tangent. So I've got the first part of my equation correct, or the first term, the first factor, right? And then I need a 1 over cosecant, or a reciprocal of cosecant. And a reciprocal of cosecant is sine. So sine x over 1 is the same as 1 over cosecant x. And at that point, I've shown all the steps that make that identity correct. Got all the way to So you should probably expect a trig identity on the exam, but I wouldn't expect it to be that hard. A little easier than this one. Okay, and I think we've got just enough time to go over the polar coordinate problem. And then we'll get out of here. But maybe I'll take a question. Yeah, the final is mostly multiple choice, but there are a couple of free response questions. They're short though, the free response questions. It's gonna be very similar to every other exam you take online. Fine. So for the final exam, you'll get 2 hours. Yep. So it's roughly double the length of a regular exam. All right, so let me set this guy up. We've got a polar coordinate that we want to turn into a rectangular coordinate, and we also want to plot it. So let me start by recognizing that -2 pi over 3 and 4 pi over 3 are the same angle, or they're coterminal angles, I should say, which means they'll be in the same position on a polar coordinate graph. So -2 pi over 3 and 4 pi over 3 should be coterminal. So if I'm trying to plot this point out in space, we're out on a polar graph, I want to adjust this thing to 4 pi over 3, which is going to be this line right here. And I want to measure out a distance of 5 from the origin. So I want to go out 5 circles. So 1, 2, 3, 4, 5. Right, so I've got a radius of 5 out there. And then I should just trace around that circle. Try it one more time. Trace around that circle to get to my point, which is right there. That's my polar point 5, 4 pi over 3. To express that in its rectangular form, I would like x equals r cosine theta, or x equals 5 times -1/2, which is -5/2, and y equals r sine theta, which is 5 times -√3/2, or -5√3/2. The last thing I do is just write that thing as a point. So -5/2, -5√3/2. So as a rectangular point, 5, 4 pi over 3, or 5, -2 pi over 3 looks like that in x and y points. Just also label -2 pi over 3 is that angle. All right, and that concludes part 2. Look forward to part 3 a little later on.